Lab 5, Magnetic Braking with Faraday by Chandler Pittman. So, a little bit about our table of contents today. First, we'll go through the introduction, which is the purpose and kind of the equations used in this experiment. Next, we'll get on to the experiment. Third will be the model. And fourth will be that analysis and conclusion. So, number 1, introduction. So, what is the problem we are trying to solve? We are solving what happens when a magnet is dropped through a conductor, in this case an aluminum foil tube, and how long it takes for this to happen. And why are we interested in it? We are interested in it because it is a real-life application of Faraday's law. Also, by completing a model, we can compare it to the real-life results. When it comes to the equations used in this experiment, we use the Biot-Savart law, Newton's second law, Ohm's law, and Faraday's law, and Lenz's law, which is essentially the same equation. And all the equations can be seen below. So when it comes to the brief results of our experiments, we had 5 runs, run 1 being 1.29 seconds, run 2 being 1.21 seconds, run 3 being 1.46 seconds, run 4 being 1.71 seconds, run 5 being 1.33 seconds, with an average of 1.40 seconds. And a picture on the right can be seen of us doing the experiment. Now, let's get into the experiment. In this experiment, we first took a magnet and used the app to determine which end was the north side. After determining what the north side of the magnet was, we held the aluminum tube vertically and dropped the magnet through the tube, catching it on the other side. This process was run 5 times, and we recorded the amount of time it took to go through the tube. The following times were recorded below. The length of our tube was 46.5 centimeters, and the width of our tube was 0.007 centimeters. Next, let's get into our model. Looking at our model, we can see step 1 was first putting in the geometry of the tube as well as the properties of the magnet. We then create a function to calculate the magnetic field of a bar magnet, and then also create a function to calculate the magnetic flux. In the next step, we use this one line to calculate the current in the ring, and then below it, we use the next 4 lines to compute the typical B field at each ring. Finally, we calculated the net force on the magnet as well as updated the magnet's velocity and position, of course by applying Newton's second law. So, when it comes to our model results, we can see in the top left the tube being created. This was an example of the model of the aluminum foil that we used. We can see that the time in the tube was 1.465 seconds according to the model, which means our measured of 1.40 seconds wasn't too far off. And if we look to the right, we can see the graph of velocity versus time. And we can see that from around 0.2 seconds to 1.4 seconds, it has a velocity of around negative 0.31 meters per second. Finally, let's get into some analysis and conclusion. So, let's look at some analysis and conclusion. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? If the resistivity of the conductor was reduced as close as possible to 0, stronger magnetic fields would be generated due to the Biot-Savart law and Ampere's law, which would cause the magnet to fall through the tube a lot more slowly. So, for example, our calculated time of 1.4 seconds would be more than that. It'd be a lot slower. And finally, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So, if holes or slots were cut into the tube, the magnetic force would be a lot weaker, causing the magnet to fall a lot faster. This is due to the fact that it is messing up the magnetic fields and the forces, so if there's holes in it, it will just kind of act like that aluminum foil roll that we know it to be. Finally, let's look at kind of some assumption errors we could have made. The first thing we did to stop errors from happening in this experiment was repeatability. We made sure our experiment wasn't an outlier and that it was repeatable. So, by doing those 5 runs, we were able to ensure that that actually was a time, the 1.4 seconds, because we took the average of those times. Next, an error we could have made is there could have been outside magnetic forces that we didn't know about, and we just kind of assumed that there weren't. However, an error that could happen is there could have been outside magnetic forces, but for this case, we just assumed it wasn't. And finally, we assumed there weren't any holes in the aluminum tube, which would have messed up the magnetic fields. Like discussed in the what if question, if there were holes in the aluminum tube, or if even the tiniest of hole, it could have messed up our magnetic field. So we assumed that there weren't, and just kind of did the eye test and assumed that it wasn't. And that is all. Thank you.